Buenos días, mi nombre es Osvaldo Bascur. Hoy día vamos a presentar Digital Transformation in the Mining and Metallurgical Complexes. We are going to present Digital Transformation in the Mining Complexes. My name is Osvaldo Bascur. I'm a principal with OSB Digital and also a consultant fellow with SIG Advanced Analytics. Our agenda for today is Secrets of the Digital Transformation. We're going to show the 4 steps which are required to maximize metal recovery. We're also going to focus on how we can define a system for dynamic decision support using predictive analytics. And at the end, we are going to give 3 real-life examples of what companies are doing and draw some conclusions. Recently, I finished writing this book, Digital Transformation for the Process Industries, a Roadmap, which really focus on integrating under a data infrastructure how people have to adapt to use the new technologies and how to look for new business processes that needs to be solved to really achieve profitability in these industrial complexes. Usually we take the data from the process control systems in real time, but we need to have the right tool to transform that for performance monitoring, event management with data aggregation, so we can pass that information onto our management and look at assets through equipment condition-based maintenance. And this is the integration of the data, the time, and the analysis that is required to present these new ways of performance monitoring of industrial complexes. In the past, we had, as we can see there in the slide that we put together for another book called Smart Manufacturing, where we have the process control on one side and the business control on the other side. And these things have been separated, the OT and IT dilemma. So for that, we need to create a new group which is going to deal with this digital infrastructure and transform the data into a way that we can really do some dynamic decision support in mining operations. The traditional problem that we have today in mining is that the grades have decreased tremendously in the last couple of years, and this requires a lot more energy and a lot more water. The disturbances that we are seeing from the mine are very different than what we had in the past, so we need to be looking at that on a real time to be able to adapt to the reality that we are facing today. This was presented by Professor Douglas Festineau in 2001 in Rio de Janeiro for the Sustainability Conference. Today, the traditional transformation secrets are that we got too many silos in the operations. There are too many versions of the truth, too many spreadsheets, one for operations, one for engineering, one for maintenance, and one for management. And also management is just receiving information which is probably they won't be able to see how those assumptions were created to aggregate the data into something consistent and valuable. So we're going to emphasize on how management can be part of this decision support process, starting from the process control data. So as such, there are many opportunities to redesign the business processes for maintenance and operations to work together, from planning and economics to work together with the operational data, so we can detect the hidden losses that sometimes goes unseen in operations because they aggregate and they average the data, losing tremendous amount of resolution on the data. Keeping the right data at the original resolution is the key, but having the process and the journey on how we have done those calculations and analysis is a basic requirement in the digital transformation processes. Usually planning is not considered in the operational data, and this is what we're going to look very deeply as a big transformation on how we can assess the hidden losses, the energy, and the water, which sometimes are not aggregated at the right time with the right context to identify if there are really losses or not. Industrial plants sometimes are not integrated with an operational support, causing disaggregation or not really knowing at the enterprise what's going on in the plants. So we're going to look at that as well. This is really capturing in a graphic that management is looking at all these reports in Excel spreadsheet or some kind of other systems, but there is no direct connection with the business data and the data that they are collecting from maintenance, from engineering and operations. So there is this big gap, and we are going to look on how we are solving these days these issues. This one shows graphically how the planning and economics is on the right hand side, and then the different operations in the enterprise are on the left side. And usually you got these business targets and process targets for all the units, and then you want to have on a very consistent way what is the recovery, what are the yields, and what are the costs, what are the energy consumption, what is the water consumption, and all the reagents that are used in the mining. So really in this opportunity of the digital transformation, we see that the mineral processing plant has to be integrated 100% with the mining plant, as we're going to see in our examples, because this is what really drives the benefits that you can see when you do that. And we start this day from the drilling, the blast, the shovel, the trucks, on how those needs to be collaborated with how the mineral is going to be fed into the milling operations. So this is what we call optimizing the whole value chain in mining. Usually when we want to solve a problem, we have a lot of raw data that is coming from the process control system, mining system, and we do have the target. So we need to really monitor that, identify the root causes. As soon as we do that, we need to identify them, but we need to see what are we going to do to improve. If we are satisfied, we leave them alone. If we are not satisfied, we need to establish alternatives. And this is what we are going to be discussing today, how management will be receiving these root causes and how the engineers are suggesting ways of improving or even innovating. And we see that this is sometimes done not at the plant, but in strategic competence centers where we are looking at the maintenance, engineering, and management. And that's what we call the right brain of the decision making, and is the strategic decision making and decision support for the mining operation to minimize problems when they are not on target with the operations. As such, here we have the big problem is that when we start looking at the plant, we need to make sure that they are coordinated. So the stockpile, the grinding, the rougher, and the flotation needs to be all in what we call the blue regions. The blue regions is what you are within the budget, when you are within the planning. The orange is when you have troubles, and these are the hidden losses, and we need to account for those. So we need to aggregate the production, the energy, and the water for those, and stabilize those before we can do any optimization of the whole chain supply. If we grind too hard, we are going to have a lot of fine material that produces rheological problems in the milling, in the classification, and in flotation. If we are on the other side, as this was done and detected by the research done in Australia at the JKRC, Lynch presented this many years ago. They did a big analysis, and it's called the elephant curve. So if you grind too coarse, that liberation is not correct, and you are going to end up with a lot of metal going down to the tails. So it's very important to manage, as we see here, the size distribution, and make sure that the size distribution has the right target for the flotation to maximize the recovery. And we are going to be looking on how we can do that today with the new sensors and the new soft sensors that can be calculated with the operational data and using online models. Usually the data that we have from the process control system is not adequate to do advanced decision support. So we need to have the right sorting, the right cleaning, assign the right context, and the right context in terms of time to do the real analysis and create the performance models of recovery, of grinding, and managing the silos that we have in a metallurgical complex. Really, information is really the combination of data and events. And this information transformed with models enable us to define the insight and the corrective actions that are required to maximize the recovery in a mineral processing plant. So for that, we have come up with a new tool in which we have the SIC, which is divided into 3 pillars of the workbench, where the process engineer can transform that data into really understandable information that can be passed on to management or decision support, and we call the organizer, where document what we did and how we did it and what the opportunities that we might see to avoid the hidden losses that are being detected and presented. At the same time, having such amount of information, we can use all the data science which are embedded into this platform, so we can define the cross correlations and identify as we're going to see new ways of controlling the plant and managing these constraints that are sometimes being violated. This system collects the data from Pi systems, from Honeywell system, from Aspen Tech, and so on, and the data is still residing in these systems, but in this SIC cortex is where we have an environment where we can analyze and do advanced analytics and predictive models. So basically what we have in Workbench, which is what the engineers, is the new tool, is the new Excel, is going to enable to do profile searches. So those are the different time frames in which the unit are operating right, not right. So we can do and perform different type of analysis, and then we can apply regression methods, ordinary least squares, principal components, logistics equation, so we can model and predict when we are going outside the windows of operation, which are defining the right procedures to operate the units. You also have external calculations, so you can transform the signals into something more logical than just having a snapshot. And of course, you can venture into going in advanced Python programming, where you can use all these new algorithms that are available to really fine-tune the models that can be created by process engineers at the first level. So there is a real importance where we go from guided analytics and machine learning to script-based analytics and machine learning. So both coexist, and that's how you really go through the journey in the digital transformation in any industrial complex. So the first step to get started is really to identify the business understanding, the data preparation and organization, which usually resides on how, let's say if you have Pi, on how Pi needs to be organized correctly so the tax becomes available for everybody. And then you can calculate these hidden losses by catching when you are not operating at target. Once you have this subset of data, operating right, operating in trouble, downtimes, idle losses, or in maintenance, you can really fine-tune your time series and use that subset of data for advanced predictive analytics using the latest modeling tools, where you start understanding what are the major variables and how to avoid these losses. And after that, when you get that, you can implement that in the plant, and you put these findings and you deploy them by defining the right business processes, so maintenance gets to see ahead of time when something is going to wrong, so you can plan accordingly if you need to shut down the plant, or you can wait for another day or two before you have a downtime. But eventually you can synchronize the whole chain supply to maximize your yields and reduce the operating cost. This is the first thing that we need to do, as I said, is to organize the data in these digital twin concentrator models. And we're using the Goldratt theory of constraint to really synchronize from the um, material coming from the mine into the crushing, the stockpile, then we get the grinding, and then usually we cause problems in flotation, but most of the time those are due to major changes in ore hardness, on the size distributions, or fines that we had because the mine has been, now we mine much more complicated material than we had in the past. And at the end, we can have sometimes problems in the thickening, and thickening is very important to recover as much water as possible. But if we do have the right size distribution that we can create in the grinding to both liberate the material and to really have the right size distribution for the thickening to extract as much water as possible, as we can see. Then the thickening goes to tailings, and that's why we have a lot of waste, because if you consider that you have 0.5% copper in the feed, usually what you got on the waste is the 99.5 amount of material that is waste and needs to be sustainable operated. And of course we get our concentrate that will have as much copper, as much moly, and all the precious metals that are contained in the ore. This shows an example using SICK in which we have created the plant. As you can see on the left-hand side, we have all these objects which are doing all the calculations in real time and enable us to see and to aggregate the data when you have these impurities, let's say pyrite in this case, there are very clearly sees when you analyze the inputs to the concentrator, the changes in mineral density, and you can see how the recovery has been fluctuating due to the changes in pyrite or in the density of the mineral. It's very evident. But what can you do? So those are the things that we are going to be focusing on, and that's where you do the continuous improvement and innovation that we are going to be talking to identify why we got all these orange sides here, which are the ones that you are really going into trouble in some of the units. And the idea will be to have only green bars, and this will show you the total production by unit, the energy consumption by unit, and the water consumption by unit. So then the second step is to really aggregate the data when you got those disturbances and to identify the hidden losses and see exactly how much money you are losing while you do this operation. And this is really how you're passing the raw data that was done for process control, how you're passing that into the decision support system to really see what you can do. And what you can do really is to model the things so you can predict what's going on so you can avoid problems and either increase the production rate or decrease the production rate, right at the right amount of waters, reagents, and be on top of the situation so you can really maximize and reduce your operating costs. This one shows the results that the manager will be seeing for the whole plant, and you can see here the production, the hidden losses, the water losses, and the electricity consumption losses, which is really when you are operating and you are using the energy, but you are not getting the right outcome on your recovery, and you are probably getting a lot of copper in the tails. So collaboration between the process people, maintenance, is really very important. What I'm showing you there is that little cube that really says how we are going to see that and how the manager can get involved to really see how the engineers and the subject matter experts were able to present this information to them. So by clicking on that and operating on the web from the cloud, most likely, you can go to the next step and you can really see what the engineer was able to do and aggregate the real-time data and identify the losses when you were not operating on target. All that information is basically identified here in a journal where we have all the details on how the engineer was able to come up with those results that we're presenting to management, changing completely the culture on how we operate in these operating plants. And the next step, when you got this subset of data, when you are operating good, when you are operating bad, you can really develop models for prediction so you can avoid problems. So we take here an example of a mineral processing concentration plant, and we do have the particle size distribution of your feed material to the SAG mill, the output of the cyclone, and eventually there we got a grinding module or grinding model that we can operate here to identify what are the right amount of water to maintain the size distribution which is really required for the flotation. This is the flotation requirement, and this is the feed, and then we can have additional modeling tools that we have available to predict what is the right size distribution that we need for flotation to really maximize the flotation, and then what are the right amount of waters that are required to get the right rheology in the mill so we don't have grind out or we have cyclone roping. And this has to be done very quickly, almost in real time, so we can have an assistant to the traditional control systems. So we understand the losses, so we can fine-tune what are the processes that we are using to get the operators the right instructions and set points that are required for the whole plant. We also calculate using cross-zero detection the recovery, so you can predict what is the recovery for the different type of ore, for the different type of size distribution, and what are the effects of the flotation in the system. This is just showing some of the results that are very evident that it's not the P80 that we want to control, which is really the size distribution, as we mentioned it in the original slide. And that size distribution is critical because these days that size distribution, due to the changes in hardness, is changing, and that changes the viscosity, which really stop the capabilities of the traditional grinding systems, roping in the cyclones, and of course that coarse material or fine material affects also the pulp density in the flotation, getting also some rheological problems in flotation, as we have been studying recently by the Froth cameras that are available. This is a typical flotation bank in which we have the power, we have the air, we have the frother. Very importantly here is that we are using an hydrodynamic flotation model that really calculates or estimates the air holdup, which is a very important KPI for flotation, because the more bubbles you have at 1 millimeter, the more attachment you are going to have, so capturing as much copper and all the associated metals that will report to the concentrate, minimizing the losses in the tails. And by being able to have this cross-zero detection and this advanced analytics, we can calculate the recovery in real time to be able to model that and to see exactly what are the levels and the turbulence that we have in the first two cells, in the other two cells, and the other two cells. So we come up with a profile of air holdup and the turbulence and the velocity and the amount of air that we need, and what is the frother that we need to maximize the recovery. So this one is showing just an example on when we got that data and these feature variables which we just described, having the air holdup, reportation profile, we can optimize the recovery, as you can see there, because we see the calculated recovery with the predictive recovery. So we are really understanding when we move a variable, what is the effect on our calculation, and also on our calculation, and also the estimate, the real-time estimate on how things are being manipulated. For the grinding, which is the most important area of any plant, in mineral processing plant, where we are liberating the material, we can also see the ore type, the stockpile effect, the SAG mill, the ball mill, the amount of power that we are using, which is really doing the comminution, and also now we are including the power that we are using in the flotation, because that's the one that creates the bubbles and create the right interface, because that holdup is all based upon what we call the flux theory, where we got an interface which is depending on the two-phase flow that we have embedded in the predictions. This one shows you how the data would look in a table, where we have for every bank each cell and air holdup that we can look at as one of the indicators that will maximize the recovery that we are calculating in real time. And as such, we can also calculate the losses. An important thing that we are showing in this diagram is that we got a lot of Froth cameras these days, so those are available. And this is very important information that we can, as you can see here, we can interpret that using these machine learning tools to see what is the Froth telling us in respect with the operational data, so we can put that together in the models as we advance in today in these mineral processing plants. So then we look at the findings is that now we can have what we call a plant model, plant process identification model for optimization. So we know all the variables which are evident that are contributing to the recovery. So we have, for instance, the P80 size square, we have the particle size shapes of a tertiary cyclone for the tertiary grinding, the effect of the primary cyclone for the secondary grinding, and the particle shape of what's feeding the SAG mill. So by having these shapes of these, we can really improve what is the right size distribution that we need and what is the right percent solid that we need for the flotation at the right turbulence that we are obtaining, what is the right level of each bank to get the right turbulence, so we have the maximum flotation possible, so we understand what are the variables and what is the settings that we need to do for our process control system. This is a case study from ArcelorMittal. You can look at his videos. This is Michel Prour, the direction of system. They have a competence center now over the years. It took about 5 years for this to happen. They started doing the optimization of the concentrating plant. This is iron ore in Quebec Cartier. But then we looked that the major problem was really the way that we're doing the blasting. So the blasting contributed a lot to get the right blasting, so we get the right feed to the SAG mill, to the autogenous grinding, and to the gravity separation machines. And then definitely all that part really transformed the way that they are analyzing the mine and the mill up to the port. The port before had a lot of issues due to the loading of the ships. So by looking at the whole integrated chain supply, by looking at the operating times of all the machines and looking where the constraints are, you can maximize the throughput throughout the complex, and the benefits here have been more than $120 million. This is the results that were obtained a few years ago, as you can see, and this has been maintained and evolved into a much more sophisticated center that you can look at some of the things that ArcelorMittal have been presenting about this topic. This is basically a screenshot of how the drilling, the loading and hauling is being analyzed to maximize the throughput at the mine, and then again have the right size distribution, the bin full, so they can simplify the feeding to the grinding and the gravity separation for obtaining and maximizing the iron ore concentrates. And then after that the pellets, and after that loading the chips that goes into the steel mills. Here we got into the Barrick Gold. It's another case where we implemented these same ideas. We got the homogenization of the stockpile to feed the right material into the SAG mill, into the grinding, and then the cyanidation to get the right size again, so we have the maximum amount of gold being recovered. As you can see here, they augmented the recovery. We presented a paper with Jacob Stein and Barun Gorain at the SME a few years ago, so if you want to read a little bit more, there is quite a few additional information that you can get. And on the other side, we got also Anglo American. Anglo American implemented this using a slightly different technology, but with the same concept of this digital twin, applied to 14 concentrators, 3 smelters, 2 refineries, and 9 geographical areas. The major goal that they had here was really to decrease the overall energy consumption in reducing the cost. And this was done by looking at many type of opportunities that were done in grinding and also flotation. And the most important one that really contributed tremendously was the community integration with their power generation company, so they know exactly when you got a shutdown of a SAG mill or a big machine, how then the plant can go into maintenance. The power generation can really articulate how to contribute their energy demand and supply in this large metallurgical complex. So this is really an implementation from an enterprise perspective that has resulted in tremendous benefits that's still going on after probably now 7 years. So to summarize here, the role of data and seek advanced analytics in the digital transformation is very important. The integration of the OT and T is a very important aspect on how we can do these things. And then we got the transformation of data into information, so engineers and managers can really collaborate in identifying how users can easily use this data in a very practical way to look at opportunities for improvement. So the digital transformation is a journey. It's nothing that you do in one shot. You need to transform the way that people are working, the way that people are collaborating. People will have to do a lot more work as process engineers using Workbench. They will need to do some programming. This is not for IT people. This is really for the new generation of metallurgical engineers, mechanical engineers that need to understand how their units are operating. And those subject matter experts are really empowered by using these new tools. The business processes that we discussed are very importantly transformed because we get a much integrated aspect on how we plan the way that we run the mill according to the type of ore and the type of mining processes that we're applying. As we discussed, the blasting becomes tremendously changed when you have the right drilling and the understanding of the ore, so you know exactly what type of blasting you need because you understand the ore much better than ever possible, so you start commuting and doing your grinding at that level, so you have the better grinding at front and the better grinding for the flotation or your separation processes. And of course the technologies need to be embedded, they need to be made very easy to use so we can increase the visibility of the unknown and of course improve the overall operational effectiveness and also including the sustainability, so we reduce the amount of energy, the amount of water, and maximize the copper or the whatever metal you are trying to recover. So thank you very much. If you have any questions, please let me know and we will entertain any that you might have. It was a pleasure speaking with you.